If you are going to leave, I wonder if you could kindly be quiet. Thank you. Now that I've made a dent here. My name is Janiele Maffei. I am the president of the Earthquake Engineering Research Institute, EERI, and it is my great privilege to introduce to you today our distinguished lecturer. Before I do, I wanted to say grazie mille to the Italian hosts of today's conference, of this conference. It really is remarkable, and the city is beautiful. But our speaker is a dynamic speaker with an outstanding topic, and I know you're going to be excited to hear this. MiCo Olsen is the CH2M Hill Professor of Geomatics in the School of Civil and Construction Engineering at Oregon State University. He obtained his BS and MS degrees in civil engineering from the University of Utah and a PhD in structural engineering from the University of California, San Diego. His research focuses on the collaboration application of geospatial technologies to natural hazards, as well as infrastructure monitoring and management. He's participated on several post-earthquake reconnaissance teams, particularly some interesting work in New Zealand, including 3D point cloud data to document damages, the impact of rock falls on dwellings during the 2011 Christchurch earthquake, liquefaction-induced damage, was also part of the team that developed seismically induced landslide hazards. Michael has a long list of amazing affiliations, including with National Science Foundation Rapid Facility, Cascadia Lifelines Program, the Cascadia Region Earthquake Science Center, editor at ASCE Journal of Surveying Engineering, and is the CEO of a tech transfer spin-out company, Easy Data MD, LLC. It is my great pleasure to introduce MiCo Olsen, and I do hope that once again the guests that are leaving could maybe get a little quieter for our outstanding distinguished lecturer. My pleasure to introduce MiCo Olsen.
All right, thank you to all you brave ones sticking it out to the end here. The pressure's certainly on following Jack and his excellent presentation. Just moments ago, my wife sent me a picture of my youngest daughter sleeping and said, don't turn your audience into that. So hopefully you guys are energetic and full of fun. I know stand between you and dinner, but appreciate you being here. I'm very grateful for the ERI committee for bestowing this honor on me. I'm still kind of in a state of shock, and I'm grateful to have this chance to talk about some topics that are of great interest to me. And I think of very strong importance to the earthquake engineering community. So thank you, and thank you to the conference organizers. Before I get too far into the presentation, since we started a tech transfer company, basically developing software tools for point cloud data, OSU requires I put a disclaimer in front of each presentation so you can decide whether you want to listen to anything I say or not as a result of that. But kind of to get started, I wanted to kind of give a little bit of background and context for where I'm coming from on a lot of these thoughts and observations. And so I got involved in earthquake engineering a lot thanks to Steve Bartlett, a professor at the University of Utah. Did a lot of work with Les Yout and lateral spread mapping. And I thank Jack for talking a lot about the importance of displacement and deformation, because we're going to talk a lot more about the measurements than you probably ever want to know that really determine those. And that was one topic he always hit home, was the measurements that were made for the lateral spread models and how detailed and how variable those measurements were compared to what you actually see in the models and what really went into those. So he convinced me to join ERI, which is what led me here today. $20 student rate, and getting all the Spectra issues was a strong point there. So after that, I decided, yes, I want to be an earthquake engineer. What am I going to do? I'm going to go down to San Diego and be part of the program there where they have the shake table and all these awesome earthquake engineering facilities. Well, a project came up that was a little bit of a detour from earthquake engineering. It was studying sea cliff erosion on the beaches of San Diego. So I had a choice. Do I want to look at a bunch of spreadsheets from tests, or do I want to go hang out on the beach for my PhD? I chose the beach, and so that's where I ended up. And I learned a very valuable lesson in that process. I learned that the more you monitor something, the less likely it is to fail. So I put a picture up there of Torrey Pines, one of the sites that we started the project. We said, this is going to be awesome. We're going to get so much good data of sea cliff failures and collapses happening here and so on. Years went by, nothing happened. The week I left to go to Oregon State University after being at UC San Diego, that's when the big failure happened and everything collapsed. So as soon as I stopped monitoring it, it all fell apart. But working with Neil Driscoll and Scott Ashford and others at UCSD, I got a chance to kind of get exposed to laser scanning. That then I continued on working with Falco Kuster, who I'm fortunate to be here in the conference as well. And so got involved with another kind of side detour of coming here to Italy, actually, down in Florence, and studying some historical buildings, and got introduced to working with Falco on the visualization side and kind of saw the potential there, but also worked with Maurizio Certacini, who was a researcher of a biomedical engineering background, but specialized in art history, and would do lots of different scanning and capturing paintings with different wavelengths. And kind of through this process of this interdisciplinary group that I was working with, came up with the idea of a digital clinical chart, which was essentially the idea that we have all these structures that we live in, that we rely on, that are important to us, both physically and culturally, but we don't really have good records, right? We go to the doctor, what do? We get all sorts of tests done, all sorts of records, they have all sorts of fancy tools. What do we do with our buildings? We only complain when something goes wrong, right? And so really that idea of, can we collect these really good baseline records so that in the event that something happens, we can react quickly instead of being, just trying to figure out what happened and if there actually was deformation or something that happened there. So it was a really great experience working with Falco and Maurizio on this, and that kind of will formulate a lot of things for my talk today. So got to OSU and started working in laser scanning, and about 2 weeks into the job there, the tsunami hit in the Samoan Islands. And Rob Cahan, who was kind of the lead for gear and doing all the sorts of laser scanning work, was not available to attend. And so they're looking around, who's got a laser scanner? Oh, Mike Olsen. Well, actually, I didn't have a laser scanner yet because we had ordered one at OSU. I just started, but it wasn't due to arrive for a few more weeks. But thanks to a company, David Evans and Associates, got a scanner in hand and went and deployed to American Samoa. And so that was kind of the first reconnaissance effort I got involved with, and started to see the value of getting these systematic measurements and these very detailed information. After that, it was busy. Those years, you had 2010 Chile, 2011 Japan, the Canterbury earthquakes, Nepal, Kaikoura, Alaska, kind of all happening over the years. And I said, we can't keep up with all the scanning that needs to happen and all the data that needs to be collected for all the different teams. And so about that time was when I was able to connect with Joe Wortman and Jeff Berman at University of Washington and several others to form what's called the RAPID facility through the National Science Foundation Natural Hazards Engineering Research Infrastructure. And so this was a chance to basically train researchers to collect their own data with the laser scanner. So help them understand what are fundamental procedures that you need to follow, what are the good surveying principles that need to be put in place in order to collect good, high-quality data. And so the RAPID facility has been a tremendous resource to put these tools in the hands of the community and put in place. And Jeff Berman's going to be here giving a talk on the RAPID facility on Thursday in the LiDAR session that I hope you can join. But really a good chance for collecting this data, putting it, as Ellen mentioned earlier this morning, onto design safe so it's available for the community to use and really understand these observations. Because one key thing is I go out and collect data that's maybe important to me, but I'm not collecting information that's important to everybody else with traditional techniques, right? I may measure the width of a beam or a column or something of interest to me, but I'm not capturing that whole scene. And the advantage to this is going out with these higher quality technologies, we're able to collect data that's useful to everyone and has a lot of downstream applications. And so in the title I put, how can we save the world using geospatial technologies? And so I'll talk a little bit about that today, of how we can digitally save the world and some of the applications associated with that, with the superpowers of laser scanning. So what are some of the challenges? First thing that you always hear people say, well, we'd get a laser scanner, but it's too expensive. Well, in my talk today, I'm going to say you need one. You basically can't afford not to have one in your possession, given the high return on investment of the technology and all the different uses. Big challenge we have is there's rapid change in technology. What the scanners I was using just a couple years ago are pretty much outdated with the current technology and different ways that we can collect the data. Sometimes there's disillusionment. Somebody tries out a new technology because somebody said it was really great and they didn't get the results that they wanted, right? Because either somebody didn't know what they were doing in the collection, the technology wasn't quite there and was oversold, all sorts of different reasons happen. Also talk a lot about some of the workforce shortages and some of the impacts in restoration associated with this in terms of our surveying workforce. As well as I think you have issues in priorities today of what people find important and what they want to invest in, and the general resistance to change, right? So we always see those kind of as barriers. Well, in the geospatial world, there's a lot of opportunities as well to address some of these. And so I think it can support our planning efforts to make sure that we're better able to respond to things. We can identify our vulnerable infrastructure, and then we can digitally preserve the different structures, right? We can't retrofit every single building that's important to every single community, but we can digitally capture these, and we can put those in place so that at least we have a record of what was there, and then afterward decide, should we rebuild it, or is the digital record sufficient to really help us understand what life was like, or whatever was important about that particular cultural structure. As well as in post-disaster reconnaissance, these tools are invaluable for the information there. So right now we're in the midst of a geospatial revolution where throughout engineering we're seeing applications of geospatial technologies in many different forms and many different applications. A whole ton of new technologies being unleashed, and different ways that those technologies can be implemented to support different activities. Now, the challenge is there's a lot of variability in the accuracy associated with the technologies and their different capabilities of what they can produce. And we're also seeing a shortage of education opportunities in geomatics and in geospatial education. So it's kind of this irony that the technologies are becoming much more available, but the core fundamentals and understandings of how to really collect good data is being washed from our curriculum. And so I think there's a ton of opportunities there, not just turning people into button pressers to say, hey, I can hit a button and collect information with an instrument, but really understand how to put things together and achieve higher accuracies. So we have a lot of potential with that. So we have, I think, this thing we face called the technology adoption cycle, where we start out, we need something faster to get our job done better, right? Everybody's always looking for that. We start to get word of, here's an application or a tool that somebody told me about, sounds like exactly what I need. And then you go and get that tool, and it turns out the vendor lied to you and said, oh yeah, it's capable of achieving such and such accuracy, and then the reality is it didn't quite work. But then you seek out expertise and you figure out ways to squeeze that accuracy out, you're happy with it, and then a little while later, right, oh, it's not fast enough, it's not getting the data I want, I need something different, right? And we kind of go through this loop a lot of times. And this is one thing I see kind of happening a lot in the industry, is we're collecting a lot of data with laser scanners and even photogrammetric methods called point cloud data, just basically representing the 3D scenes. But we also have a lot of people that are overselling, that really haven't gone and understood the fundamentals, that go out and collect data and then sell it to you as if it was really good data. And it looks great, it looks beautiful. And so I've coined the term pixie dust to describe that data that is just kind of a magical data, but not really grounded in proper survey and control procedures. And so use that stuff with extreme caution, and that's, I think, why it's important we maintain these educational opportunities in surveying in our civil engineering program, is so that as engineers, you know what to look for, because it's getting harder and harder to tell the difference between good data and bad data, and good surveys and bad data. So as these data sets have evolved, we've formulated a lot of, I think, kind of really cool opportunities in using these to help understand things in engineering. So one thing I'd like to kind of talk about at the planning stage is the Cascadia Lifelines program, which is a group of lifeline providers in Oregon that have come together to really talk about the interdependencies between their lifelines, as well as develop different tools to help prepare for the large earthquake we expect in the Cascadia subduction zone. And geospatial technologies have been very prevalent in this. So one of the things we came initially to the group and we said, hey, we want to develop all these new liquefaction mapping procedures for you because we think that's what you need. Turned around, they said, well, we just published this major report, the Oregon Resilience Plan, but we don't have access to the actual data. We have a little PDF map here that we can look at and try to, stretch and squint at and maybe determine the values off of, but we want the data. So we turned around and developed a WebGIS platform with it. And since then, some others, Ben Mason, Armin Studline, Ben Lashinsky, and Matt Evans, and several students have worked to develop a catalog of databases of boreholes of about, I think they're up to 9,000 boreholes in the database now. And so they're able to do some really cool spatial analysis tools by having these data geospatially located and tagged correctly That was a big problem they faced initially, as things were tagged to the wrong coordinate system and had to reconcile all that. But now they've got tools where you can do digital drill rigs and basically pick a spot and then basically get what the borehole log most likely will look like at that slot with uncertainty bands in terms of SPT values and other things with it. And so this helps us really plan out better site investigations. It's not meant to replace doing any due diligence and collecting the geotechnical data, but can augment it, that information. Because I think the two things that always get skimped on a project, one is the geotechnical investigation, and the second thing is the site survey. And what are the two things that create problems down the road? There was a utility there you didn't know about because you didn't spend enough on the site survey, or there was a bad layer underneath that caused settlement or some other problem. And so I think those are some things we need to rethink investing up front to not pay the price later on. We can also take those databases information to apply them to fragility curves and do geospatial analysis of what's happening to the network of the system, what's happening to, in this example, to the pipe network, and really building in a lot of the concepts of performance-based information, but applying them across a large area. And so one of the things that was put together as part of CLIP is basically a fragility database, looking at different types of lifelines, different types of fragility curves to support them, and how those could be used. So one example of that is applying it to landslide displacements. Basically in Oregon, we name our landslides. We've kind of run out of names because there's so many of them, you just go from one landslide to another. But they're a major source of concern for seismic activity, and particularly closing out lifeline corridors as we go throughout the state. And so we can really use this information to better understand what infrastructure is at risk and what infrastructure is most vulnerable as we move forward. So digging a little closer into higher resolution, higher accuracy type applications, we've seen an explosion of terrestrial laser scanning and UAS drone technology in order to capture data. And there's all sorts of different applications. This is just a subset of the different applications. But one of the key phrases with LiDAR data is collect once, use many times, because it supports so many different types of applications and different ways that it can be used in reconnaissance activities, whether we're mapping cracks, whether we're trying to get an idea of what sort of concrete spalled or what happened. And I'll show kind of some examples of those with it. But really the key of why I'm pushing these technologies so much is they really help us see the full picture. I think a lot of times in the way we collect information is we'll take a picture and we start to lose context of what that object is relative to the rest of the scene. What is it connected to? What are other features in the area? So this is a way we can digitally preserve the scene quickly before rebuilding efforts occur. It also helps push us away from basically plan and profile mindset in engineering into full 3D analysis and hopefully push us towards new methods. I think one challenge we have is sometimes with the new technology is we say, well, it didn't give us the number that I want for this particular metric, which is how we do things. Well, that metric might be outdated. You know, a lot of times we get very focused on high accuracy at one single point, and maybe we can determine that very well with other technologies, but we have no idea what's going on in between those points, and the reality is a whole lot more uncertainty is introduced from the fact that we're not sampling things at high enough resolution with it. And so I think this is a way that we can push ourselves forward in the engineering community, develop better and improved models, and really start to understand the context of what's going on at this site. So now you need justification to go back to your work and justify buying a laser scanner. So I said you can't afford not to have a laser scanner. So a lot of times in especially earthquake engineering, we're always trying to make the case of why should you invest in retrofitting this structure now, or why should you invest in doing this? And I think one of the important things we need to invest in is the monitoring of our structures, and that all starts with having really good baseline information. Whether we're talking a building or a highway network, we need to know what's there, what condition it's in, and everything like that. And so with these new technologies, there have been a few studies that have come out recently that have shown really crazy returns on investments associated with these. So for example, Oregon DOT went and took a look at their 3D, basically the process of doing 3D design in order to reconstruct highways and do new projects with that. And they looked at the return on investment on it, and that isn't a typo, that's 2,269%. Anybody got a bank account yielding something on that order? I think we're what 2% now if we're lucky on our bank account. You know, over 2,000 times percent return on investment from the money they put into switching to do 3D design to what it's paying out in money that's saving them now. So they also found that when they're using machine control and construction automation, they have a 416 times higher chance of a pass on their grade compared to not doing it. And so these technologies will pay for themselves really quickly with that. They're collecting mobile LiDAR data on a biannual basis across the state, and they found that it's a greater than 2-to-1 return on investment. So yes, the initial system cost them $1 million, but they've been able to yield at least $2 million in returns and money that they've saved as a result of investing in the technology and applying it. Another study was developing techniques for using mobile LiDAR to evaluate pavement marking retroreflectivity, which is very important to us as humans, but becomes even more important for autonomous vehicles that are using those to track as you go through different lane changes and other features. And so they invested in a research project for that. One project using the results of that research more than paid for that particular project. And so these examples go on and on of the importance of investing in that data, and I think in particular in context of our engineering, our initial site analysis, we need to do a better job collecting this information more detailed, both before the project starts as well as during the project when it's going on, and then after the project, so we have that information. Spreading to nationally in the United States, we have the 3D elevation program with the goal of collecting LiDAR data continuously across the lower 48 states, as well as INSAR data and other forms in Alaska. And a study coming out on that recently estimated a 5-to-1 return on investment of the money that was invested in this program versus the returns that we're seeing through all aspects of the community. And so there's huge opportunities in leveraging this data and putting it in place. And so kind of moving into part of the theme of the talk here is the technologies are paying for themselves. We have a lot of different features and important historical structures that are very vulnerable to earthquakes. And there's been huge efforts in terms of documenting and collecting this information, but it's a tremendous effort, and there's not enough time or funds or resources to really capture all these different sites in our current implementation. So there's efforts like the Earth Archive, which the goal is to cover the whole entire planet with LiDAR-based data and get really detailed point cloud data across the entire planet, or SciArc that is specialized on basically millimeter to centimeter resolution on historical structures or features. So why is this important to do? Well, a few years ago we had the fire that happened at the Notre Dame Cathedral, right? And one of the key instruments in really rebuilding that historical treasure was having survey data available, having detailed point cloud data available. Just so happened a few years prior that basically some researchers at a university had gone in and scanned the structure. And so that became the most important data in terms of helping them understand what things look like and really being able to start working on the rebuild effort, which will take some time to do. So now the question is why do we need to be reactive to that and hope that we got lucky in this case? Shouldn't that be a given that we have this data readily available and collected in the event of something like this happening at a structure? So there's lots of ways we can use this historical data. We can do lots of different types of virtual reality assessments with it. Virtual reality technology has become cheaper and cheaper and a lot easier to work with. And yeah, I think in the early days, a lot of people were disillusioned with this kind of technology, but that was because it was really, look how cool this is, right? And so on, and it never got really beyond that. But now there's tools coming out where you can perform measurements, perform explorations in 3D, start doing all sorts of different types of analysis with it, instead of just moving into, just looking at the data, really what information can we interrogate? And particularly as we get more into these 3D procedures, it's really hard to do these kind of things on your traditional desktop computer because you're seeing a compressed image and you don't really get that appreciation for the scene. And so I think as engineers, it really helps us understand what's happening, what's going on. There's all sorts of amazing tools out there be developed by a lot of different research groups that are hopefully making their way into practice. One of the sites that we scanned in Nepal after the earthquake was the temple in Bhumati, and so the data here was very useful in terms of doing an analysis of this historical pagoda structure. And so Ricky Wood led a lot of efforts of basically taking this and looking at the inner story drift and getting those displacements and measurements out of it, and really kind of starting to characterize what happened. Now, one big challenge we had in this is this building's been around for a long time. There have been many earthquakes. So what were really truly the baseline conditions, right? We don't know because it wasn't scanned before, so we have to make assumptions in those cases. And so the more we can get that information, the better we'll be. The Gamu wastewater treatment plant was another one in Japan. And so we've collected the information here for forensic analysis after the tsunami waves hit this plant. And pretty much kind of finished up the papers, finished up the work. This was going into the tsunami load provisions in ASCE 7 as one of the structures to be modeled to verify that the equations were working correctly. Well, a couple years ago, I get this random email from them saying, you know what, we want to turn this into a monument and a site, and we recognize it's going to degrade over time. Do you happen to still have those laser scans, with the information of how it was? And so we were able to pass that information on to them, create a website where anybody can go and access the data, and use that to really kind of preserve that memory of what happened with the earthquake and reinforce that in generations to come. So as I mentioned, some of that data was used to the calibration of ASE 7. I'll leave it up to you to guess which ones are the SAP models, the structural analysis finite element models that were done, and which ones were the laser scan data. So it was important data to verify that the equations were producing reasonable estimates of what those magnitudes of deformations were, as well as the patterns and distributions of those. And you can see that the models overall were performing pretty well compared to it, but there were some deviations that led to some changes in terms of those developments. Other examples is mapping out different bridge structures in Dichato, Chile, one of the bridges that collapsed over the Biobío River, and we can map out how much are those columns leaning, how much are they deforming, what are the extents of the landslide, where are things moving, what's the direction of lateral spreading, what is the magnitude of lateral spreading, and again, all these things kind of change across the area. Another example is in our backyard, and at landslide, as I mentioned, we have names for a lot of our key major players. This is Arizona Inn landslide in southern Oregon on the coast. This thing fell in January 2023, right about the time the PhD student that was developing these GPS sensors on site was about to defend, so he had to wait another 2 years. No, I'm just kidding, we didn't make him wait. But it was a good case for his dissertation defense because he was able to basically capture this as it happened with his different systems that were in place to monitor the slide. And we had, fortunately, about 6 years of data prior to it, so we could kind of see what those trends were and what led up to the failure. And you will notice in the bottom right image, bottom right, is the landslide was very kind enough to basically form the tension cracks around our GPS sensor, but leave it in place and leave it pretty much close to plumb at that point. So we're able to get really good information. But the system, it's about a $500 GPS system that we're able to put in place. This was the key piece that ODOT was using in the rebuild operation to know when it was safe to start the construction operations, when it was safe to send people down this 200-foot shaft. Well, it was 200 originally. They found out it was 100 feet after the landslide sheared. But they had this information to know when the landslide was moving so that they could perform those operations safely. And so these investments up front pay huge dividends down in the future. So this is just an example of some of those deformation patterns across the slide, looking at the different vectors of movement happening based off several UAS surveys. And in the bottom right, you can see that things were pretty slow for a while, but between 2021 and 2022, we start to see this uptick of movement and acceleration before the massive failure happened, right? So if we can start identifying where these points are, where things are starting to reach a point of no return, we can maybe reach that point where we can be reactive at that point and figure out a solution before the catastrophic failure happens and it shuts down the highway for weeks and then months with basically repair operations. Going down to Canterbury, New Zealand, after the Christchurch earthquakes, we hear a lot about liquefaction, and that's kind of what goes to everybody's mind, but there were also a lot of rockfalls that happened with it, particularly in the Port Hills facility. And so using laser scanning technology to capture all these different sites and in these different buildings and houses, we're able to get how far did that rock go into the house, and then use those to develop fragility curves to look at what are the risks to residents living in certain areas, and use those as a planning resource to identify where people go in the future. Or GNS Science was very proactive about collecting data. Unfortunately, they didn't have terrestrial data before the first earthquake event, but they were basically scanning these sites for several months after the earthquake happened. And using this database, we're able to look at what were those rockfall trends with time, and found that there was basically about a 5 to 10 year period where there was an uptick in rockfall activity at these particular sites. And so that leads to a lot of needs for increased maintenance and other things with it. So jumping up to the Kaikoura earthquake that we heard about as well in some of the previous presentations, this I think was kind of one example of really the value of these data sets to bring people together. So for the longest time, the map was really what brought people and communities together, right? It told you where people were located, how to get there, and what sort of resources and other things were in locations there. And it's the same with these digital geospatial technologies. So in this case, we could collect the data. There's a tunnel that has information helpful to the structural engineers. There's geotechs interested in the landslide movement and rockfall activity, transportation engineers interested in the road being shut down, as well as coastal engineers from the tsunami and those impacts on this particular coastal site. And so really quick with one data set, it can be basically that one data set to rule them all, right? To really bring everybody together so that we're all looking at the same page and the same sources of information. So I've seen a lot of great excitement of happening in that through different resources like Converge and all the different EERs, GEARs, SEERs, and all these different groups that have really strived to bring the communities together to collect this information. So now, while we've seen a lot of progress, we're missing one key component in emergency response that we need to look at. And so who's ever put a puzzle together and found at the end that you're missing a piece? You know, it just happened a couple of months when I was putting one together with my son. Turns out that there was a piece missing there from the bottom. He did it. He didn't tell me when I took the picture, but he just wanted to have a picture with the missing puzzle piece because he likes to cause trouble. But that's one of the things that I think we're missing in a lot of the earthquake engineering community is we really haven't had these conversations with the surveyors and really had these discussions of what's needed and what needs to be put in place in order to collect this information. And I'll talk a little bit about kind of why that's important. So one big challenge that we have is surveyors are becoming an endangered species. And some of you have tried to buy property lately all throughout the world, have found that it's very hard to find a surveyor to come do your property because they're just too busy and there's not enough of them to go around. So this plot is the number of licensed surveyors in Oregon. You can see that there's been a decline since year 2000. And basically, if we keep extrapolating that curve to 2030, we'll be all out of surveyors. But what do surveyors do? Well, they're the ones setting the property boundaries. They're the ones that are basically doing the construction quality control assessment, locating things, doing the surveys for the designs, verifying that things are built in the right location, and then recording that as built after. So when we're talking about recovery, we're losing a workforce that is vital to getting all the reconstruction efforts put into place. And so they're going to be critical to that particular effort. And so we need to find some ways to reverse this trend so that we have a stronger workforce. That's not enough to convince you. Some of you have probably seen in the news, property owner in Hawaii basically went there to their property that they bought and discovered that the contractor had built a home on their property, $500,000 home. They weren't supposed to build it there. The contractor was supposed to build it on the next lot over. What was their excuse? Well, we didn't want to pay for a surveyor, so we just kind of built it, right? So now it's in a big, huge legal dispute, and you know the lawyers always benefit in this case, right? But the general public doesn't. And these is just one kind of very simple example of what happens. But when we start talking about emergency situations, when everybody's stressed and things need to happen quickly, these mistakes compound. And especially if our contractors are saying, well, I couldn't find a surveyor, or hey, I didn't want to pay for a surveyor, those problems happen, and then we're going to be dealing with them for years to come. And although I'm showing this from a kind of a US-based perspective, these trends are happening internationally. We used to always look and say, well, at least Europe and Canada have very strong geomatics programs, but there's also been a lot of challenges and declines with that. And particularly in our civil engineering programs, we've seen less and less surveying principles and measurement principles being taught over the years. And so right now in the US, about 2/3 of the programs have a surveying course as part of the required curriculum for a civil engineer. 1/3 do not have anything in place with that, and that's a huge loss for those as well. We're also going through a crisis in terms of geodesy, and I won't spend all the time going through what's the difference between geomatics, geodesy, geospatial. I'll tell you more about that after if you're really interested in knowing the details between those. But probably most of you have used GPS in one way or another, whether you know it or not. It's pretty much ubiquitous in everything that we're doing. Well, GPS requires a lot of complicated math and geodetic principles in order for it to operate. And the National Geospatial Intelligence Agency in the US is facing a severe shortage in terms of workers. And at one point, it reached the point where they only had 2 PhDs on staff to handle all the geodetic math to support the GPS system. So think about that for a minute, just 2. One of them was about to retire. And so they started to realize we are in a severe state that we're not going to be able to maintain it. Yes, we've got a really strong GIS workforce, but they're not necessarily qualified to have all the information in the planetary physics in order to run GPS. And what would happen to our community if that were the case? You know, one, we've got all the navigation issues that were lost, but GPS is really the workhorse behind a lot of our infrastructure projects. And so they put together this document, the Geodesy crisis, that's gained a lot of traction in reversing the trend, and fortunately have been able to hire, but they're basically still needing to hire a lot of people and expand to get up to the capacity that they need to support the geospatial economy, which is a $1 trillion a year economy. All right, so now why am I getting so heavy into this? And this I think is one challenge that we face of why we really need the civil engineering education and in a lot of fields to understand the basics of measurements. We use measurements for a lot of things, and we don't really think twice about what the measurements really are or where they come from or what they represent. We just say, oh, this so-and-so said this was a measurement of displacement. But we don't really have good detail of what the from was, what the to was, what the method of measurement was, was there a slant distance or anything in between there. And so this is a fun exercise we like to do with high school teachers when they come and do an outreach activity, is we tell them to measure the length of a football field. And I apologize for being here in Italy and using the term football improperly. We're talking US-based football here. So lots of people will have lots of different things that come to mind, in terms of that. And it's kind of interesting to see how much the results vary when we ask them a simple question, right? Should be 100 yards. Well, some people will measure that from the top of the end zone to the top of the end zone. So a lot of people come in with that number. Others measure it from the end of the end zone to the end of the end zone. Others measure it the whole length of the actual field surface, right? Because it is the field. I said measure the length of the field, not necessarily the playing area, right? So that's how they interpret it. And others say, well, I'm going to measure the whole stadium and give you a number. And so these numbers are all over the place. And I think it's very common in a lot of the measurements that we use that we do this without even thinking about it. What I may be measuring in a building is I may want the distance between one wall and another. I need to know whether that's the edge of the wall or the center of the wall that I'm measuring the distance between. Some cases, some people will measure it across the field in the transverse direction as well. And so there's lots of different ways that this happens and lots of different uncertainty. And we can't just basically assume that somebody else is going to do the measurement or do the survey in the way that we think it needs to be done, or the way that we would proceed with it. So the question is, where are we teaching these kind of basic principles in our engineering curriculum? And unfortunately, we're losing a lot of that expertise. And so it gets even harder when we start thinking about the higher accuracy type applications. So now when we're talking about that white painted line, are we talking about the center of the line? Are we talking about the front edge of the line? The back end of the line, right? All of those have different sorts of implications. And so we need to make sure that those things get accounted for. So why do these matter? Well, we have higher and higher accuracy applications that we're trying to support. And so a lot of things that we could just kind of gloss over in the past now become critical, especially as we want to get that deformation magnitude. We want to look at those very subtle deformations, because that's the difference between whether somebody can inhabit the structure or not, right? That's the difference between whether it's safe or unsafe. And that gets harder and harder to measure. And so this is where we need to start really thinking about the instrument quality, the user skill, the calibration, the correction, whether we're doing repetition as measurements, and even more advanced adjustment computations. And so all these things make a big difference in whether we can squeeze out just that little bit of accuracy. It's very easy to go from meter level accuracy to decimeter accuracy, but then when we start talking about centimeter accuracy, it's orders of magnitude more effort. And then when you want millimeters accuracy, it's even orders more of effort beyond that. So as we start kind of collecting these data and using these different measurements, sometimes they go together like peas and carrots, and I'm doing this in honor of Steve Kramer. He had a famous lecture on apples and oranges, and so I kind of took a little bit of license with that. So sometimes we're taking measurements and maybe slightly different, but they still blend together when we're putting them into our models, and we don't notice any difference. Other times they're like cats and dogs, right, where they fight, they don't agree, and that's oftentimes one of the reasons why some things aren't working from one model to another, is they're based off of a different set of measurements, and it may be a very subtle difference between those. But then as we start talking, was it a 2D measurement? Was it a 3D measurement? What was the spatial variability of those particular measurements? And a lot of times that information's lost. Then we throw in the fact that the Earth likes to move on us. And so we're trying to reference all these measurements to a datum or a reference frame or a system, and that moves. We have tectonics going on under ordinary conditions that are causing things to move around and shift, but then we have large earthquake events that actually change the location of the center of mass of the Earth. So what does that do to our GPS satellites? It changes their orbits, right? It changes all these reference frames that we developed, and so they have to be updated frequently with that. So this is just one example of the Indonesia earthquake. Changed the location of the North Pole, it decreased the length of the day, 2.68 microseconds shorter in the day. That's the reason why I don't get anything done anymore. That's why I blame it on that, right? But for GPS timing, that's a huge error source, right? And so it throws all these different things off, and it also changed the shape of the Earth just a little bit. So it's very important that we account for these things, because otherwise, if we're doing repeat monitoring surveys and we're not accounting for tectonic motion, we're making erroneous change detection assumptions. So we can no longer sit there and bury our head in the sands and put things into place. We need to really start thinking about these things and incorporating them in our reference measurements. And one pivotal learning experience for me for this was when I went down to Kaikoura after the earthquake. And there's all sorts of aftershocks, rebound effects happening. So they were updating their GPS station coordinates on a daily basis. So I came back afterwards, gave a presentation on this to our local surveying chapter. And they said, well, we get mad at the National Geodetic Survey because they update coordinates on things on us every 10 to 20 years. I can't imagine what it's like, getting those things updated every day. But that makes a big difference in positioning when we're talking about what those reference stations are. And so the Land Information in New Zealand has a really good documentation on here's what you need to document in terms of your time of observation, time of processing, what version of the software was used, and has really great guidance for their surveying community. But then the question is are we ready? And so kind of as a follow-on to some of the local surveys, we asked them, what was available? What guidance do you have in terms of your role in emergency response, given that you're going to be critical to do these surveys? And they're scratching their head and saying, I have no idea. Nobody's ever talked to us about this. We had this massive plan, an Oregon resilience plan, that was a really great effort to really help us understand our infrastructure, but there was absolutely no discussion in it of the surveying and mapping. Oregon DOT put together manual after manual of their emergency response plan, and all they could find in there is one line that said, the surveyors are going to be responsible to do surveying and mapping after the earthquake. That was it. So then they just said, all right, that's clear, right? We know what we're supposed to do, right? There was nothing about procedures or what was really important or what they needed to do, who they handed the data off to, or any of those different things. And so they've been working on a working group to kind of build these things into place, and soon we'll be starting a project looking at UAS post-disaster guidelines to kind of make a difference there. But we've got a lot of changes happening in terms of our coordinate systems and reference frames that I think are very important for the engineering community to be aware of. These are US focused, but the same thing happens internationally with the reference frames that are used. But one of the big changes that we made recently in the United States is we got rid of the US survey foot. And many of you are probably saying, I've never even heard of the US survey foot. What is it? It is not 0.3048, basically meters to feet. That's not that same conversion. That's the international foot. So we've been using two definitions of feet in the US, and most people are not aware of it. And so it becomes a big problem when software doesn't have this corrected and other things. And so finally we got to that point where we've corrected it and now said moving forward we're only going to use one definition of the foot. Apologize to all of you internationally with it, because you're probably scratching your head and say, why didn't you guys go to the meter? Well, the answer is if you ever want to know that, go to a construction site in the US and ask one of the construction workers, how deep is that trench that you're doing? How many meters deep is that? And then you'll see where you end up after that, right? They're just going to say, you go in there, talk to me in feet or don't talk to me, right? No, unfortunately, we're not quite there yet, but we're making progress on that definition. And for those that are from the state of Texas, you're happy to know with the change from going from US survey feet to international feet, Texas is now 4 feet bigger than it was. And so, yeehaw. Or I guess that's more of a cowboy thing. So there's lots of initiatives and things underway pushing this forward. There's lots of resources now, including the ASC survey manual and surveying conferences that are happening to kind of bring awareness to these kind of things with the community. But this is something I think moving forward that really I encourage you to reach out, is really get to know the surveying community and bring them into your resilience planning, bring them into these engineering discussions. Talk to your local schools in civil engineering and really make sure that they're getting the surveying education as a fundamental part of it, because otherwise it's going to be chaos after the earthquake. Things are going to be out of control. And for those of you that are survey, there's a nice pun in there for you, because surveyors rely on control networks, right? All right, it's too late in the day. You guys aren't laughing, so I gotta work something in there. So future, this is kind of one thing that I think of where we really need to go in terms of the data that we're collecting and putting things in place, is we have a lot of really cool 3D mapping systems out there, and ways to share data and share information. We can stream these really dense point cloud data sets through the internet. You basically catalog where the photographs were taken, so now we have those photos in context. Have you ever scrolled through your list of photos and trying to remember, now was that column over here, was that column over there, and trying to sort things out? We can use this location-based information so we know exactly where that column was and what was going on around in that column, because we now have that point cloud data located there. We can also store our measurements in there. So if I'm somebody interested in landslide displacement or coastal erosion, I can go in there, make my measurements. Somebody else can come in and look at it and say, oh, that's what he did. This is what he used as his reference point, and this is what he measured to. Instead of, I just said, well, it was 5 meters, and trust me that I made the measurement correctly, right? So then you can look at it and say, yes, I like how they did the measurements, but no, really my model needs this measurement out of it. And then you can go in and extract the measurements that you need. And then moving beyond that, not only getting that measurement, but getting that uncertainty tagged with it. So was it 5 meters plus or minus 10 centimeters, or was it 5 meters plus or minus 1 centimeter, right? And then that starts to help us really understand the uncertainties that get propagated into the models that we create, and really push to move things forward. So some of the key points right here: start collecting your baseline data now. LiDAR sensors, we have them on iPhones now, believe it or not, on some of the newer systems with that can collect good data. There's limits to it, so I'm not saying that's the end-all source, but for some applications, it's one of the tools that can be there. And we basically need to start this initiative of really capturing our assets and our features and our buildings and getting this detailed information so we have it now, so that after the earthquake, we can really start to understand, did things change or not? What sort of deformation was there, right? We're in performance-based design, where that deformation is one of the key signs of damages that things are experiencing. And especially for our vulnerable sites, our really precious cultural, historical sites, let's capture those now before they're lost due to an earthquake, so that we have that record. So we're not just saying, well, that was fortunate that the cathedral stood, or that was fortunate that the city hall stood. Let's get those captured so that we have that information, and if necessary, we can use that in the rebuild process after, and really restore that sense of community and that hope to the community as a result of it. Invest in geomatics and geodetic education. Make sure that gets propagated through our civil engineering curriculum, as well as increase the number of geomatics programs throughout there. I think is something that's critical to provide the workforce that is going to be instrumental in terms of our recovery and making sure that things can open up, things can be rebuilt efficiently, and as well as improve that communication between the surveyors and engineers, which I think is sometimes can be a bit rocky, right? I go to engineering meetings where they bash the surveyors, and I go to surveying meetings where they bash the engineers, right? Oh, they're not doing it right, or they don't understand this, and so on. We really need to improve that dialogue, because in those stressful situations, that's where things are a problem. And I also think that a challenge now is to know our limits. The technology has become so easy to use that you're literally pushing a button, but all the reference frames and datums and all those things that really determine whether the data are accurate or not, that is the complicated part, right? So know when you're comfortable with it, when you know you're getting good data, versus when you should hire somebody that has that expertise in it. And then the last part there is we need to change our ways. Sometimes we evaluate that new technology and say, hey, it didn't work with the metric that I need. Well, maybe there's a problem with the metric, so there's no reason why we can't question those particular metrics. Maybe it is the case that technology didn't work, but sometimes we need to change to more advanced metrics in order to move our industry forward with that. And so just kind of a parting thought, I see geospatial information serving as that unifying glue to enable meaningful collaboration between science, engineering, and public policy, necessary for a resilient society capable of effectively responding and adapting to natural hazards. And so this is really the way we can bring people together. We can all get on the same page in terms of the analysis that we need to do. So with that, I'm very thankful for the sponsors of the conference and organizers of the conference, and EERI for this incredible honor, as well as many other people who have assisted me in this. These are logos from different collaborators at different institutions that I've shown their work today, or funding agencies that have supported it. So a lot of the really cool stuff came from me. All of the cool stuff came from them, and the boring stuff came from me, right? So appreciate all the great opportunities to have to work with so many experts in the earthquake engineering community. And with that, thank you for sticking it out to the end here. I know it's been a long day, and appreciate you being here, and wish everybody a good evening.